Now that you've learned the formulas for pH and pOH, it's time to actually do a few problems to see how these can be used. We start with an acid calculation using the strong acid, chloric acid, made from dissolving hydrogen chlorate into a specific volume of water. This is a strong acid, which means 100% of it is going to ionize and form hydronium, meaning that if 100% of it ionizes, the concentration of acid that we start with is going to be equal to the concentration of hydronium that we make as it ionizes. Every pH calculation that you do in Chemistry 11 will use strong acids and strong bases because the calculation of pH and pOH for weak acids and weak bases requires a tool that isn't taught until Chemistry 12. In order to find what the pH is, we need to figure out what the concentration of H3O plus is, meaning that we need to find the number of moles of HClO3 that we add into water and divide that by the solution volume. The problem is that we're only given mass. We're told that we start with 5.56 grams of hydrogen chlorate like this, meaning that we would need to divide by this compound's molar mass. So if we go to the periodic table, we see oxygen has a molar mass of 16, chlorine has a molar mass of 35.45, and hydrogen has a molar mass of 1.01. So if we do some quick arithmetic, we can find the molar mass relatively easily. 16 times 3 is 48. And if you check my arithmetic to make sure I don't do anything wrong, the molar mass should come to 84.46 grams per mole. Now, the next step is not strictly necessary, but remember that pH is always the concentration of hydronium with the negative log, so we should convert this from chloric acid into hydronium just to make sure that we have the correct units. So here we have our moles of hydronium. The concentration we can find by dividing this number by our solution volume in liters. And then finally, to figure out the pH, we take our concentration of H3O plus and take the negative log of it. And if you do this in your calculator should read approximately 1.06 as the pH value. This looks correct because we're dealing with an acidic solution, and remember that a low pH always indicates that you have a more acidic solution rather than a basic solution, and vice versa for a high pH. Now, it seems a little bit weird for us to calculate pOH of an acidic solution, but if we remember that pH plus pOH is always going to be equal to 14. So to figure out what pOH is, all that we would need to do is take our pH number that we calculated here and subtract it from 14. If you do this, this number will come to approximately 12.94, again indicating that there is a relatively small amount of OH minus, which makes sense because this is an acidic solution. In the next practice problem, we're going to deal with a basic solution here. So in this case, we're dealing with a metal hydroxide, in this case, strontium hydroxide. Important thing to note is that strontium hydroxide contains 2 hydroxide ions per molecule that we have, meaning when it dissociates into strontium 2 plus and 2 hydroxide ions like so. This will be important when we're calculating the number of moles of OH minus that we have. So again, because we need to calculate concentration, we need to get our original mole number, or our original mass number rather, of strontium hydroxide converted into moles, which means that we have another situation where we need to divide by the compound's molar mass. So if we go to our periodic table, strontium has a molar mass of 87.62, which we can work into some quick arithmetic like so. We have 2 oxygens, so that's 32 grams per mole, and 2 hydrogens, which is 2.02. And if we work through this calculation here, you should find that your molar mass comes to 121.64 grams per mole, which tells us the number of moles of strontium hydroxide. But remember, if we're calculating pOH in this case, because we're dealing with a basic solution, what we're interested in is hydroxide. So we need our second conversion factor here, multiply by 2 hydroxide per 1 molecule of strontium hydroxide, and that tells us our moles of hydroxide. To find concentration, all we do is divide this number by our solution volume, which is 0.375 liters, and we have our concentration of hydroxide. And since we're dealing with a basic solution, we're calculating pOH, meaning that if we take the negative log of this number, we would be finding pOH. If you put this into your calculator, this comes to approximately 0.476. So this is less than 1. Remember that pH and pOH are going to be a number between 0 and 14, and this is a very small number, which means that this solution is very, very basic, meaning that there's a lot of OH minus in the solution, but that makes sense because for every 1 molecule of strontium hydroxide, we get 2 molecules of OH minus. Finally, we need to find the pH, but we can use the relationship between pH and pOH in order to find pH by simply taking our pOH that we calculated here and subtracting that from 14, which in your calculator comes to approximately 13.524. The reason for 5 significant digits, when you add and subtract, it's key to always preserve the same number of decimal numbers so that your measurement is equally accurate, even if the number of significant digits is different. The final situation that we're going to work through is actually in a neutralization reaction. So in this case, we're taking a solution of potassium hydroxide and neutralizing it with hydrochloric acid in order to get potassium chloride and water, which again shows that the solution has been neutralized. The problem is that this neutralization only occurs if the moles of potassium hydroxide and hydrochloric acid are equal. But here, we're given 2 different measurements, meaning that this is actually a limiting reagent question in disguise. However, because we're calculating pH, it's treated a little bit differently. So in this case, we still need to find out the amount of H3O plus and OH minus that we are going to make. So in this case, I'm going to start with acid because it's only one calculation we need to do. We have 3.50 moles per liter of HCl, which means because HCl is a strong acid, this is going to ionize 100% of the way to give us 3.5 moles per liter of H3O plus. We can multiply that by the volume of our acid solution, which is 0.250 liters. And if we do that, we find that our moles of acid come out to 0.875 moles of H3O plus. On its own, this doesn't mean anything. We need to find out how much hydroxide we're working with here. And again, we are given a mass measurement. We're not told what the concentration is, so we've got one more molar mass calculation to do. Periodic table says potassium has a molar mass of 39.1. So if we work through some quick arithmetic here, we can find that our molar mass of potassium hydroxide comes to 56.11 grams, which we can divide our initial mass measurement by in order to find the moles of potassium hydroxide. And we know that potassium hydroxide is going to give us 1 hydroxide ion per potassium hydroxide. We don't really need to write this in, but it's good to keep our units clear. Now, here, we actually need to find the number of moles of hydroxide that we make, and if you put this into your calculator, this comes to approximately 0.178 moles of OH minus. Now here we can see that our moles of acid are clearly greater than the moles of base, meaning that HCl is our compound that is in excess. Now, because we have more acid than we have base, all of the base here is going to be neutralized, meaning that we are going to have an acidic solution because the excess HCl is not going to have any OH to neutralize it, and therefore that is the only thing that is going to influence the pH. So the next thing that we need to do is we need to find out how many moles of hydronium will be left over after this number of moles of hydroxide neutralize it like this. Now, to calculate pH, we need to take our moles of hydronium and divide it by a solution volume. But since in this question we're mixing a basic solution with an acid solution, we need to find what the total volume is going to be, which I'm doing right now. Fairly simple calculation. So, if we calculate that our total volume is 0.725 liters, we have now found what the concentration of leftover hydronium is going to be, and all that we need to do is take the negative log of this number in order to find what our pH value is. And if you do this in the calculator, you'll find that the pH value is quite small. This comes to approximately 0.9. Sorry, wrong number I'm referring to in my notes. This comes to, it's even smaller than I thought, 0.0172. So this number is almost zero. This means that there is quite a lot of hydronium left over, and that makes sense. We have significantly more hydronium than we do hydroxide, meaning that our solution is going to be very, very acidic. Now, if we want to calculate pOH, the only thing we need to do is 14 minus the pH value that we calculated here. And if you put this into your calculator, this number comes to approximately 13.9828. Again, keep the number of decimal places the same when doing adding and subtracting. In the next video, we're going to look at a different type of concentration calculation, not involving pH, but involving a type of calculation in which we want to find out what an unknown concentration of acid or base is in case we want to test and find out how dangerous solutions can be.